Okay, so I'm just going to skip this part. You guys have probably all seen this if you've seen the building thermal models. This was simulating specific thermal hardware, just how to do honeycomb panels, how to do insulation, and then how to do constant conductance heat pipe models. I will talk a little bit about this one because it's useful. The quick way that I've found to simulate heat pipes is basically model the flange, make a vapor node that is arithmetic, has no mass, and then do a node to surface conductor where the value for that is based on a watt per linear inch Kelvin heat transfer coefficient for evaporation, condensation for the different sections of the heat pipe, and scale it by the fact that you're multiplying by an area. So if the width is 2 inches, I divide it by 2 so that when I do the multiplication, I get really a watt per linear inch in this. That then lets you also fail the heat pipe because I could say, let me set this conductance to 0. If I have that set to 0 and then I make this a heater node, now I have a failed heat pipe. The other way you could do it is you could use FlowCAD, model a pipe there, but the drawback to that is if you use FlowCAD, now anybody else who inherits that model and uses it also needs to use FlowCAD. So for the very basics of a heat pipe where I'm just trying to dump heat into here, conduct through the vapor node out to the condenser, this is probably a good enough way to do it. You just have to remember to do the per area so that it scales the conductance value times the area of each subpart that it makes. Again, when you take the width into account, it now becomes a watt per linear inch for each segment of the heat pipe. And then you would have, the flange here would have a thickness that's appropriate to what the extrusion cross-sectional area gives you in the material. So that's the way I would deal with heat pipes. And seems to be good enough for most purposes. All right, so radiation calculations. This is definitely an important part, so I want to make sure everybody understands this. So a Monte Carlo ray trace is basically a random event or sequence of random events. I begin with a random point on a surface, and I fire a ray in a random direction with 100% of its energy. And I trace that ray until it intersects the surface. Once it intersects the surface, portion of the energy that's associated with that ray is deposited on the surface based on the properties. So in this case, it's 70% absorptance for an emissivity. So 70% of the energy associated with this ray is assigned to this node. And then the ray is reflected. Now, it may be reflected specularly, which means that it's going to have an angle of incidence equal to an angle of reflection. Or it may be reflected diffusely, which means it's going to pick a random direction. The way that it determines this is it generates a random number. And if that random number says, hey, it's a specular reflection based on your specularity, that's how it reflects it. If it's a diffuse reflection, then it picks a random direction and it continues propagating on. So now when the ray leaves this surface, it only has 30% of its energy and it then goes out to space. So once it leaves the system, it's now energy that's lost to space. So I fired one ray, now I fire a second ray, random direction, goes here. Again, 70% is absorbed, and the remaining 30% of the energy is reflected back out to space in a diffuse manner. This one is the third ray that I fired, and it immediately went to space 100%. So if I combine all three of these, this is what I get, and I would look at a Bij to space. I would say, all right, well, I had a total of 300% for 3 rays. 0.3% went to space from the first ray. 0.3% went to space from the second ray. 100% went for the third ray. So 0.3 plus 0.3 plus 1 divided by 3 gives me a view factor to space, or a ray interchange factor to space, of 0.5333. From 1 to 2, I would have 0.7, 70%, 0.7 again, and 0. Divided by 3, 0.4667. So this is essentially how you're getting Bij's, tallying up the total amount of energy that left one surface and got to another surface. And so, as it bounces around a bunch of times, even though there may not be a direct view factor between two surfaces, through reflections, there can be energy exchange. All right, so one of the things it does is it uses something called octcells to accelerate the intersection tests. So if I were to take this room as one octcell and I divide it by a plane like this, a plane across the middle, and then a plane here, I've now divided the room into 8 cells, oct cells. So what I'm going to do then is I'm going to look and see what is in each oct cell. So if a ray's over there, I don't need to check if it intersected anything in this oct cell. So what it is it's a manner of limiting the number of intersection tests that it has to do. So what it does is it keeps dividing each oct cell smaller and smaller and smaller until you have reached a maximum number of levels to go down, or a maximum allowable number or maximum allowable number of surfaces inside the cell. Now, one thing to be cautious with is don't make the number of surfaces too small, because if I have 4 elements here and then 4 ribs here, well, this node here is in contact with 8 surfaces. And it doesn't matter how small I shrink the oct cell about that node, there will always be 8 surfaces in that cell. So you don't want to do 3 surfaces, or we'll keep dividing without making an improved oct cell. So when it has done all of the, or when it's fired a number of rays, it will statistically determine whether it's fired enough rays or not based on the error that you asked for when you solved. So there's a weighted error. The error for each ray, or I guess for each Bij, is numerically defined as this. So it goes down as the number of rays goes up. Smaller Bijs have larger errors, and this is essentially the confidence interval based on a 90% confidence that I would be within that error. And so this is the error for a Bij, one Bij between 2 surfaces. What I'm going to do then is I'm going to take each Bij multiplied by its error, sum all those up, divide it by the sum of all the Bijs, and that is what we call the weighted error. And so you'll notice there's a update frequency or number of rays to fire before checking. That's usually about 5,000. So thermal desktop's going to fire 5,000 rays, and then it's going to do this error check. And then based on what it has from that first subset of data, it's going to say, okay, I need 20,000 more rays for this surface, and I need 10,000 more rays from that surface. And so it's going to then incrementally fire more rays as it needs it until it reaches the maximum number of rays, or it meets the error threshold for your weighted error that you have. So that's why you might see it go through and solve one, and then say, okay, now I need to fire more rays for this subset of surfaces. And now I need to fire more rays for this smaller subset of surfaces. So it's trying to intelligently figure out how many rays it needs to fire without having to check the weighted error too often. Because if I did it every 5,000 rays, well, I might be wasting a lot of time checking something knowing why would I check it in 5,000 if I know I need 30,000 to get close to the error? So now in the end, I have a whole bunch of Bijs between all these different nodes. So how does that Bij become a rad K? So rad K, as we know, is the area times the emissivity times the Bij. But reciprocity says that it's also the area of J times the emissivity of J times the Bji. So should we use Bji or Bij? Well, in this case, thermal desktop uses both, such that if you have a Bij but not a Bji, there will not be a rad K. If you have a Bji but not a Bij, there will not be a rad K. So it uses a weighting factor of the inverse of the error squared. So this error term here gets squared. The inverse of that is used as a weighting factor. And so the rad K that you see between node I and node J is based on the error from I to J times the area emissivity Bij plus the area of J, emissivity of J, Bji times the error from Ji squared divided by 1 over the error squared. And you can actually go through and mathematically check that thermal desktop is giving you that, because they tell you the Bij and the Bji as a comment after each of the rad Ks. So you could go through and figure out what the error is, knowing how many rays were fired for that, because it tells you that in the log file as well. So knowing the Bij term and the number of rays, you can get the error. You can then go through this math and check that, yes, indeed, that's what it's doing. Now, there's always the question, how many rays? Like I said, I start with 35,000. This gives me, a 2.65% error for a 0.1 Bij, a little less for a higher Bij. The thing you need to consider is, do I really care if I have 100% error on a Bij that's 0.000001? Is it really going to matter? So yes, I may have a really large error, but it may be such a negligibly small term that I don't really care that much about it. And as I said earlier, if you end up spending a lot of time calculating all these small couplings and then remove them by not outputting it, what's the value in calculating all those rad Ks? So it really comes down to what can you tolerate as how much time it's going to take to run your rad Ks and how many rad Ks you need to output. It's runtime versus accuracy. There is no single answer that applies to everyone. One thing I did want to go back, because I don't think I touched on it here. So to address your question about the cutoff. So what happens when this ray gets to a small enough percentage of energy, which is the cutoff? It will either be completely absorbed or completely reflected. That way it can't keep losing tiny amounts of energy. So the 10% that is Thermal Desktop's default, I find a little high. I like to say it's 1%. So when a ray only has 1% of its original energy left, at that point, it's either completely absorbed or completely reflected. So if it's completely reflected, it'll bounce and it will eventually be completely absorbed by something, whether it gets out to space or gets absorbed by the next surface. So yes, it's a slight error in there that you're not taking into account that energy, but again, you're down to 1% of the original energy of the ray out of 35,000 rays that you may fire. So did that address your Bij cutoff question? Yes? Okay. All right, so some other thoughts about radiative modeling. There are kind of two ways to think about it. There's radiative exchange, and then there's just emitted and absorbed. So I'm a body generating heat up here. I'm emitting my energy out into the room. You're all bodies of heat emitting energy towards me and towards each other. So we could think about it as the energy that's emitted and the energy that's absorbed, or we could think about it more as the energy that's exchanged between, say, Shinichi-san and myself. How much energy are we exchanging and what's the net flow? Am I giving more to him than he's giving to me, or are we balanced? So there are different ways to think about it, and that becomes more important as you consider the non-gray effects of energy, where you really have a wavelength dependency of the energy. For example, if I have something that's very, very cold, it's not the wavelength of energy of that, or the absorptance wavelength of that matters. It's the absorptance or the emitting wavelength of the emitting surface that's absorbed at that wavelength at the cold surface. So when you deal with non-gray, it becomes a much bigger challenge to deal with, and you usually end up having to band it into different wavelengths of energy buckets between each of them. We basically have said IR is from 3.2 microns all the way out, and UV is 3.2 microns to the left. But if you start to get into cryo regions where you've got something warm looking at something cold, it no longer is at the same spectral density of energy, and it becomes much more challenging to deal with. A couple of other things to think about. When you look at the energy that Thermal Desktop tells you is absorbed from the sun, that is energy absorbed. That's not energy exchanged with the sun. Same thing with the Earth. And we tend to refer to that as backloading. So when you run your heat rate, it doesn't care about, when you run your rad K, it doesn't care about where the sun is, where the Earth is. It's going to say, all right, the sun's over there. I'm only going to worry about the energy that's coming from the sun that I absorb. And the energy that's emitted by me in the direction of the sun, well, rad K just says, okay, that's a part of the sky. There's no sun there. It just goes out and goes off into the ether. So that's more of a backloading as opposed to an energy exchange. That's why it doesn't matter what the temperature of your surface is in terms of energy exchange with the planet. It will always be a positive heat load on you, even if you're dumping more heat to the planet than you're absorbing from the planet. because what would happen is your rad K to space would be larger for the portion of the rad K that is to the planet. So different ways to think about radiation in terms of exchange between two surfaces or emitted and absorbed. And sometimes it makes sense to think about it one way, and other times it makes sense to think about it the other way. So these can be very useful. This backload term is good if I need to try to represent, well, what's the heat from my spacecraft onto your instrument, so I can provide you a loading so that you can do your design and say, well, you could expect that I'm going to be giving you 15 watts of energy from all the things around you, from me radiating to you. And similarly, we can boil this down further to an effective sink temperature, which is really what we do for thermal testing. We're going to put a plate in front of something, and we need to control that plate to a temperature that's representative of the thermal scene that it sees in flight. So here you're taking the back load plus the environmental load and dividing it by the sum of the radiation couplings and backing out a T to the fourth relationship for the sink. So this is what we call an effective sink temperature, or an equivalent sink temperature, and it's just another way to think about radiation. All right, so after all the radiation computations are done from Thermal Desktop, it's going to spit out the HRA, it's going to spit out the .k files, and it's going to take that input along with inputs from contactors, heat loads, heaters, conductors, everything else that defines the model, and it's going to output it to a thermal model in a format that is known as CINDA Fluent. Stands for Systems Integrated Numerical Differencing Analyzer. It was developed in the 60s before I was even born by Chrysler. It's gone through various flavors and incarnations throughout the years. In that model, it's basically an electrical analogy. So instead of current and voltage and resistance and capacitance, you have capacitance, temperature, heat flow, and heat applied. And so those nodes are coupled via conductors, which may be linear. So a Q equals a G linear times the temperature difference, or radiative. Q equals sigma times the radiative coupling times the temperature difference to the fourth. Nodes can have capacitance or heat sources applied. At least one node in the system must be a boundary. That's what grounds it. If you don't have a boundary temperature, it could be anywhere above there and still potentially satisfy the heat loads. And then there's a variety of user logic that governs changing of boundary conditions, cycling of heaters and things like that to come on. And usually what we're interested in out of that is the heat loads as a function of time and the temperatures as a function of time. The temperatures to make sure we're within requirements, the heat loads to feedback, or the heaters to feedback to make sure that the power budgets are satisfied and we don't need too much heater power in order to do the mission, because that is a finite resource based on solar arrays. So I believe we're ready to launch into CINDA, although there was technically a break, but I think we blew through that. So let's go on. Good? Okay. All right, so CINDA Fluent. What is CINDA? We'll talk about that. The CINDA deck, the program flow, syntax, look at a CINDA model example, and then kind of how to run CINDA. So as I said, Systems Improved Numerical Difference Analyzer. Colmore and Ring has their version. There used to be a government version of CINDA. Space Design has its. CINDA G was Gasky CINDA. This was the one without submodels. I don't believe it exists anymore. It was bought by MSC a few years ago, but I think it has fallen by the wayside. CINDA includes a preprocessor, which reads your CINDA file, stores the data that it needs to in a binary format so that it can read it. And then there's a set of library functions that CINDA provides together with your user logic, compiles it, and accesses the data and goes through and basically runs your simulation as a Fortran program. So the CINDA deck is a text file. It contains all the information you need to solve for temperatures. But it does require a Fortran compiler or some other kind of compiler if somebody were to do something to make it work. If somebody wanted to rewrite CINDA, they could do it in C or MATLAB. But in the end, it's a collection of functions, calling those functions, and data that defines the physics of the problem. But in the end, CINDA is really just a compiled Fortran program. It's not necessarily a finite difference solver. It doesn't have to be finite difference. It's a generalized equation solver for a first-order linear equation. So it's really solving a G matrix times T equals Q. They could be any terms defined by that equation. But Cinda does have strengths over other equation solvers like MATLAB or Nastran, that it was developed to support many of the things that thermal engineers need. They've got heater routines. They've got time-varying loads. It handles radiation. It has functions for dealing with phase change. It's really tailored and designed for things that thermal engineers need. Keeping in mind, finite difference is a approximation of heat transfer. You get it down to a 1D, Taylor series expansion, eliminate the lower terms, you get your basic Ka over L. But finite elements could be used as well. This does create some negative conductances. Can create some negative conductances depending on the shapes. But it's still valid. It's perfectly good. I don't understand how it works, but it's no longer a Ka over L is equal to heat flow. So let's do a nodal representation of a two-dimensional bar. I'm going to make it have 3 nodes, and that's going to be my centroid approach. So I've got 2 resistors or conductors between here, and these would be the terms that I need for it. If I went with edge nodes, well, now the cross-sectional area that goes through is half. This node gets the top half, this node gets the bottom half. The length is the same, although it's a little different here because here I have to consider this half length here. But I get a slightly different set of conductances. And then if I go with finite element formulation, I get these diagonal terms in here as well, and you can see these. Now, for the K equal to length equal to the cross-sectional area, all equal to 1, you can see, okay, it might follow some intuition. Nothing negative in there that would be scary. But if I change the length equal to 2, well, the mathematics work out now that this becomes a negative value. So all of the conductors here are negative, these F conductors, and all the other ones are positive. So that's one of the things that will scare most thermal engineers. I don't really understand how it works. One of these days I intend to figure that out. If any of you are good with finite elements and understand this, you're welcome to explain it to me. But for the most part, I trust it. So we'll see what that does in a little bit, but just a little bit about conductors in series. The sum of the inverses, inverted is the effective conductance. Conductors in parallel, you sum them up, opposite of resistors. Resistors in series, you just add the 1/overs, resistors in parallel, add straight away. So let's talk about the Cinda deck. It's basically a text file. It's structured with different headers to define what the data is that's going to be in each header. There are 2 types of header blocks. There's data blocks, so nodes, conductors, sources, user data, control data, register data, and then the logic blocks, which are the operations block, variables 0, 1, and 2, output calls, and subroutines. These are Fortran-like instructions, and therefore look more like code, as opposed to the data blocks, which are just numbers and flags to indicate what those numbers mean. The data blocks are all processed, and the data that's contained therein is stored in binary files. Those binary files are then referenced when Cinda runs. The logic blocks are translated into Fortran, and that Fortran is then compiled together with the libraries of all the Cinda subroutines and goes through and executes the model. So it starts off in operations. That's where everything's going to begin. It'll load up all of the information for initial temperatures, capacitances, conductances, and then follow the instructions from operations until it reaches the end of the program. So again, once it's all pre-processed, generates an executable program, which then solves for the thermal data. So the preprocessor is first going to read through the Cinda deck and reorganize it into its expected flow. There's something called insert statements, where you can basically say, okay, I got to this point, now insert the contents from this file here, and then when you're done, return back and follow the rest of the instructions. So when you look at your Cinda input files that Thermal Desktop generates, there's a whole bunch of a few headers there, and there's usually the operations block, and then it inserts the CC file, which has all of the node data, conductances, heat loads, contactors, conductors. And it will next insert the radiative files that you've defined. So if you defined a rad-k for internal, another rad-k for internal, then an external rad-k, and then the heat rate files, those will be 2 files. There's an HRA and an HRL. And then any other files that you might have inserted So it's going to expand that out into one single file where it combines headers from one. So I can have a header node data in one file and a header same node data in another file, and it's going to take that data and combine it all into one header node data for that, so that then when it reads it through, it has all of the header node data together. So when it's processing and does all the pre-processing, as it makes it past the preprocessor, it's not going to check for Fortran. So Fortran can have its own things that it doesn't like, hey, you've got an if block, but you never ended it with an end if, or you've got a typo in there that Cinda doesn't mind, but Fortran would choke on. So this is where it's now going to compile. We went through this earlier when we saw the compile failure for looking for a function that wasn't found. Once it's done and it gets through the compile portion, it's then going to generate and run the executable. And Cinda is going to make sure that that model can be solved. So it's got to contain at least one boundary node, and it's got to have everything connected either directly or indirectly to a boundary. So as long as he can find its way to a boundary, you're good to go. But if you've got something that's orphaned and has no connection to a boundary, Cinda will terminate and say, unconnected nodes found. The executable program generally produces two output files. There's a save file and an out file. This one is a binary file. CNR has tools that they provide for people to be able to read it. This is what's usually read when you run the post-processing aspect in Thermal Desktop. I like the out file because it's ASCII. I can open it in a text editor. I can look at it. I can see what the data is. I go back to a comfort level here, but both of them should give you the same data. It's possible that this save file might now be a CSR, a compressed save results, I think, which is a new format that CNR introduced a few years ago that tends to be a little bit less disk space for it. So there's an option there that you have for use CSR in Thermal Desktop, but you can't have generally a save file and a CSR file. It's one or the other. Thermal Desktop can read both of them. You just have to tell it, hey, this is a CSR or this is a save file. And so what that's going to do is you're going to send whatever output you've requested to there. So give me all the temperatures every 300 seconds from this submodel or all submodels. Give me all the heat loads. Give me all the conductances, all the capacitances, all the registers. It's whatever you have requested to be solved. All right, so basic syntax, regardless of which header you're in, anything that has a C in the first column is interpreted as a comment. It's basically skipped by the processor. So you won't see that when you look at the Fortran that gets generated. Similarly, if you have a dollar sign, that is used as a comment for everything that comes after the dollar sign is a comment. That's true for M-type statements, which means Mortran. We'll get to that in just a second. If you have an F-type statement, which says this is raw Fortran, preprocessor, don't do anything, just pass this through, then you use a dollar sign to indicate a comment an exclamation point, as opposed to a dollar sign for the comment. Specifically to the logic blocks, which are code, an F says this is user-generated Fortran, don't touch it, pass it through exactly as is. M is a Mortran block. This says, hey, I want you to convert this to what Fortran would interpret. So when I say T100, that doesn't really mean a variable called T100. That means the temperature of node 100. And we'll get to it a little while later, how that data is stored as far as the internal data structures as to what that would be translated to in Fortran. Any character besides a 0 in column 6 indicates that it's a continuation. That's Fortran 77. And any non-header or non-directive inputs like a p-stop or p-start or spell off or spell on should be past the 6th column. So start in column 7. Column 0 through 5 are usually line numbers. 6 is continuation characters. 7 to 132 is where you put your code. Specific to the node conductor and source data blocks, there's something that they have called a fact card, a factor. So way back in the old days, if somebody sent you something in BTUs per hour foot squared F, and you needed it in watts per K, you would put a factor card in front of it, and everything that came after that would be automatically converted until you reset the factor. You probably won't find this anymore because everything now is generated by Thermal Desktop. It's all consistent with the units, but just know that that's there if you get anything really old. So, all right, so let's talk about what the headers are that you might find in a file, and then we will open up a file and show you what all these are. So the options data, this is where you have the title of your problem, input, output, file names, some of the options as to whether to use double precision, whether to allow mixed arrays, which have both integers and floating points in arrays or not. You'll have node data, and you'll notice these kind of SMNs after it. These means that I could have multiple node datas, but they each have a identifier after it for what submodel that applies to. So node data is going to have the definitions of nodes, conductor data, the definition of conductors, sources. Control data can be specific to a particular submodel, or it can be the global, which means that it would apply to all the submodels until it's overridden by something else. There's register data, there's user data global, user data submodel, there's array data, character array data, header operations data, this is where it starts. And then output calls, variables 0, 1, and 2 for each submodel, and subroutine data. Variable 0 is basically where you would want to put any time-dependent logic. Variables 1 is where you'd want to put any temperature-dependent logic. Variables 2 is where you're looking for anything after the solution is converged. So if I want to see heater duty cycles or heater states or any kind of what's the current state of the solution, this is where it would go. So let's go ahead and open up the sample model, and I'll walk you through what some of those ones look like.